if you're out there anything at 4 in the morning till about 9, it's just too hot. All right. So today, what I'm going to do, first, are there any questions or anything? I got a meeting today at 2:15 is the start time. It's about 10 minutes away. It's either forestry and wildlife science building or over in Coleman, one of the two. And well, anyway, if I break it off a little early today, forgive me, all right? And I'll somehow make it up today, or I'll only get a couple of. I owe you so much for time. Maybe do a special problem session or something. Just keep going for the next test. All right, now today we're in EMC, and you remember we covered the resistor, capacitor, and inductor and how they look like? And I think I put some problems up there, but maybe I didn't. They didn't appear? I will make sure I post them. Could you send me an email and make sure that I send you those particular problems? But we're going to keep on moving on, and after that, in Dr. Whitmer's book, what he talks about is really he talks about bandwidth and digital signals. Now I'm going to expand on this, but I want to take you through this part. This is not in the book, by the way. I'm going to post some notes on OneNote, but this is important you pay attention. The only guy in here, I think, the only two people that have had this are you two, because you had me for signals and systems. But this is real important, and it's not in the book, and it's not in signals and systems in general. It's something that I find very useful, and a lot of people do. It's just for whatever reason, it's not included. It's included in the EMC book I use and other places, but it has to do with a clever way to analyze signals, all right? Digital signals. So for starters, what we're after is really to take a look at the spectral components of a signal. So in general, there's no ice basket. Remind me to throw these out. Okay, sorry, right there. In general, if we have this is another weak one, but we'll go. If this is time and we have some repetitive waveform, I'm just going to do an obviously simple one, like so, that repeats itself. Let's say this is x of t here, and call this a, and x of t could be a voltage. We're going to say this is tau, it represents the on time, and this is t. Now that's a standard digital clock, a perfect digital clock, by the way. Not a, did you grab that one?
Yeah, I got it right here.
Ready for another one? It's a perfect digital clock. And it's also periodic. Now it goes on forever. I'm just going to tell you that. So in general, if it's periodic, any periodic waveform can be approximated as this. N equals minus infinity to infinity of C of n e to the j n omega naught t. Here, omega naught is equal to 2 pi f naught. And f naught is called the fundamental frequency. It's 1 over the period. This is the fundamental. And I think you all remember the fundamental frequency, right? Take the period divided by just 1 over the period is the fundamental frequency. It's called the first harmonic, by the way. So you might as well put down first harmonic, and this is F naught. First harmonic. All right. Now, if I take a look at that, and I wanted C of n just for this relationship, then I could get, if you want me to prove it, I will, but C of n by taking 1 over the period, the integral. And normally, I recommend going from minus tau over t over 2 to t over 2 of x of t times e to the j n omega naught t dt. That's called, minus. It's minus. That's called the exponential Fourier series. Do y'all remember that class? Everybody? And I'm going to go a step further too, but not yet. For now, we'll leave it. I'm going to show you how to cast this in terms of a cosine expansion, but this will be a little bit later. Are you with me at least with this? Do y'all recall? Now, this is all well and good, but a lot of times these integrations for waveforms that aren't so easy to understand, say something that's a bit arbitrary, they become tough. But here's a trick. Most signals that we deal with, clocking signals and things like that, they really can be approximated as straight lines. In other words, if we wanted a real good approximation for a digital clock, it would have a rise time, a flat point, and then a fall time. With me on that? They're straight lines. Now, this is why this technique is so very, very powerful. If I take a derivative of this with respect to time, then what do I get? Well, what do I get right here? It goes from 0 to a in an instant. What do we call that? A delta function, right? It's a discontinuity. The way it's represented is with a delta function. The magnitude of the jump is the coefficient that goes in front of the delta. So this would just be a times delta of t. You all agree with this if you take a derivative? Can everybody see this? Now keep going. What else? Then right at tau, what happens? Another delta, right? But there's one difference. It goes from a to 0, so it's negative, right? So now this one at tau would have minus a, and it would be delta of t minus tau, right? That's a time delay, correct, class? Now keep going on this one, and right here, it just, right at t, what happens? It repeats itself. Y'all see that? And it just keeps going on and on, down to delta of t minus tau minus t, and so forth and so on. But that's not a problem. Now, please watch this part. People often don't appreciate this unless they catch the details. Well, if this is true here, this is a Fourier series representation of this waveform, where the c of n that goes here is just this. It's the integral of this function times e to the minus j n omega naught t. Correct, class? All right, well, take a derivative of this with respect to t. What do you get? You get x prime of t equal to still the summation n equals minus infinity to infinity, right? But now I get what? J n omega naught times c of n times e to the j n omega naught t with a minus sign. I'm sorry, this is a plus sign right there, my bad. Y'all agree with me? Because when you take a derivative of this with respect to t, you bring out the j n omega naught, okay? Please write this down, be careful with this one. This is a tricky one. Make sure you take good notes here. I'm giving you a heads up, this is not in the book, but I will post it. So you get this, right? Now, isn't this really just a constant? So I could write that as some summation n equals minus infinity to infinity of some c of n prime e to the j n omega naught t, and then my c of n prime can be equal to 1 over the period, the integral from minus t over 2 to t over 2, and then it's going to be x prime of t e to the j n minus j n omega naught t dt. You all see how this is just a constant, and that means it can be represented by a single constant. Now you notice this form and this form are identical. It's a constant times an exponential series, therefore this constant can be found by doing this. Are you with me? Now this is the beauty of this technique, why you should appreciate it. Gotta make sure I've got everybody's attention, okay? Now the reason it's so important is, if you take a look at the integral of a delta function of t minus anything, minus any value a, times f of t dt from minus infinity to infinity, what is that always equal to? What is the delta? It's called the sifting property. Do you remember? What does the delta function do? It does nothing until it, what? Until the delta function's argument is 0, correct? And then it goes to infinity, but really if it's integrated, the area under the curve goes to 1. This is important. But it only exists at the time the delta function turns on. So really what this looks like right here, the way I like to talk about it is, this looks like the integral from really, I'll call it a minus epsilon to a plus epsilon right here, and it's going to be a limit as as epsilon goes to 0 of just f of a right here times delta of t minus a dt. Now here's what I'm saying. Because we're going to because this is only going to be non-zero when t is equal to a, correct? So I can put f of a here. I can replace t with a here, right? And then when I do this integration, the f of a literally can come out in front. And I can say this is really just equal to f of a times the integral from, I'm just going to go to a minus epsilon, a plus epsilon, epsilon going to 0. I'm going to put it that way, of delta of t minus a dt. And that's simply, this integral is 1. So the bottom line is this is just f of a. That's my point. Really, go back up here and look for a second. Really, when you have a delta function multiplying anything, right? The only thing it does is sift out the value of that anything when the delta function goes to 0, when the argument of the delta function goes to 0. Now that's the important point. Everybody with me on this one? So when you come over here, if you look at this, and you look at this example right here, just take a look at this and appreciate it. Well, for this one, I got all delta functions, right? Now, I'm going to say I can represent this series, my x prime of t, as this, and I can say x prime of t is equal to the summation n equals minus infinity to infinity of c of n prime, where c of n prime is given above, times e to the j n omega naught t, and I can say that my c of n prime that I want is really the integral. Now, I always say go from t over 2 to t over 2, but really it's over any period. So you can move this window of integration. You can go from minus t over 2 to t over 2 of x prime of t. You'll notice if I'm going from t over 2, let's assume tau is less than t. I'm going from this is the range I'm going to integrate over. Do you follow me in that class? I only have 2 delta functions I'm going to capture, these 2. Understand? Now, normally in the books they say go from 0 to 0 to t. Well, if you go, they normally add an epsilon there, but you see how then all of a sudden your integration starts where one of these deltas turns on, another turns on, right? You never want that. You always want to move your window where there's nothing changing. All right, so you go from whatever value, say whatever lower value, to whatever that lower value is plus the t, the period. So if I do this, now I have, that is really a times quantity delta of t minus delta of t minus tau times e to the minus j n omega naught t dt. Does everybody agree with me there? Please see. You all agree with that? All right, now what's that going to be? I'm going to put it over here. My c of n prime would therefore be, this is 1 over t, by the way, sorry. It would be 1 over t, right? You'll notice the a I can take out in front. Right? And then what do I get? Well, when this delta function turns on at what time, class? T equals 0. I look at e to the, put t is 0. E to the 0 is what? 1, right? So it's just going to be 1 right here. Then it's minus, this delta function turns on at t equal? Tau. So then you put in e to the minus j n omega naught tau. And that's your c of n prime that would go in this series, that would represent this. Follow me? Now, here's the next part. I'll get this out here. If I have this, well, that is just what? this is the same as this. So now we can say this is equal to Jn omega naught C of n. Agreed? Y'all see what I'm doing here? Because I'm saying that is the same thing as my C of n prime, right? See if I can. So now I can say that C of n right here is just equal to this A over T times 1 minus E to the minus J n omega naught T. And then it's divided by J n omega naught. So this is going to be J n omega naught T, because I took the J and omega. And that's my C of n. Do you all see what I've done so far? Everybody? And that's absolutely correct. Now the thing about this is I got that value without any reason to do a formal integral of anything but a delta function. When you integrate a delta function, you really don't integrate it. The only thing you do is observe what's next to the delta function when it's turned on and replace what? The value of t with the value of whatever the time was the delta function turned on. Do you follow me on this, class? This is the sifting property. It's very useful. I'm going to continue on and just show you a little bit more. Usually what we like to do is turn these functions into things we understand. And for this case, it's a neat one. If you look here carefully, I can say that C of n is really equal to, I'm going to put A over T out in front, all right? And then I'm going to take a look at this. And I see I have 1 over J n omega naught right there by itself. Then I can factor out an e to the minus J n omega naught T over 2 here. And then I have minus, I'm sorry, if I factor that out, then I have this. I have e to the J n omega naught T here over 2, and I have minus e to the minus J n omega naught T over 2 here. Do y'all follow me what I've done here? I factored out that e to the minus J, or e to the plus, no, e to the minus J n omega naught T over 2, and I'm left with that. Instead of having 1 minus e to the minus J n omega naught T, I have e to the plus J n omega naught T over 2 minus e to the minus J n omega naught T over 2. And why did I do that? Anyone? Because what? Because the sine of theta is equal to e to the J theta minus e to the minus J theta over what? 2J, right? Correct, class? So if I multiply both sides by 2J, I get this, don't I? What's the name of this, by the way? It's a famous man. Euler, right? Yes, yes. Euler's, there's 3 identities. This is one of them, right? Now, you all see that that theta is just what? It's n omega naught T over 2. So now I can replace this and say that now my C of n, now it's getting interesting. C of n is A over T, and then I have 1 over J n omega naught here. And then I have really what? 2J sine of n omega naught T over 2 here. And you can see the J's go away, which is a nicety. And that's something, wait a second, I can't, that has to be tau, my bad, this is tau. That had to be a tau, not T. I can't read my own writing. All right, we got down to there. Understand everyone, class? It's tau, it's the point where the actual delta function, it's the second delta function turns on, right? Now, there's one more step I can do. Does anybody want to take a guess at what I'm going to do next? Nothing? All right. You remember that sinc of x is equal to sine of x over x? Do y'all remember that? What was the advantage of the sinc waveform? you knew what it looked like, right? It was a funky waveform and it asymptotically dies out, right? But it's got basically a decay of a 1 over x decay, but it's got a sine waveform inside that envelope. Well, if I look at this, I want this downstairs, right? So if I multiply top and bottom by tau, right? And then divide top and bottom by 2, this gets rid of that. Now I have the argument here is the same as the argument here, don't I, class? Y'all see this? So I can say my C of n here is equal to really A over T, and it's times tau, so I'm going to show you, I'm going to break this out as tau over T here, and then it's going to be the sinc of n pi, I'm sorry, I'm going to put the pi in. It's going to be n tau omega naught over 2, or n omega naught tau over 2, either way. Now, that at least is something, hear me now, this is something that you can appreciate what it looks like, right? And remember, there's an n omega naught here. Okay, just write that down. I did this for a very easy waveform to understand. I'm going to show you the next waveform we're going to do this for, and this is the one that's used almost exclusively when you talk about digital clocks and digital waveforms to approximate it and then do spectral analysis. So please watch this next bit. I did this one just to get you going, and you can see how that would be the value, right? All right, for C of n. And you could easily take a look at this as n increases. Really, you have n times this quantity. N tau omega naught over 2, tau omega naught over 2 is a constant. As n increases, you're going to see the value of that the magnitude of that asymptotically go down. And you can take a look at that in a second. But next, it's going to rain anytime in the next couple hours, guys.
There's a chance of it, I think.
Anybody just jump on that some weather app, because I need to know if I got to take an umbrella with me.
20% chance.
Alabama. Chance means good chance. In July and August. I've actually gone jogging before, looked out, just a couple of clouds in the sky for a 45-minute run. I came back and I was drenched. It happens that quick around here.
It's just a bunch of little tiny storms. They're in Montgomery right now.
Well, let's stay there, but there's no telling. All right, now I'm going to give you, this is the one you make sure you follow me on. And I'm going to use that technique of taking the derivative to get the value of C of n, all right? Please watch this. Here's the real clock. This is the clock cycle that everybody talks about. It's used everywhere. If this is the axis of time, and we're just using x of t in the general sense, it's usually a voltage, an input voltage, but it doesn't matter. Usually the waveform looks like this. It's approximated as this, where this would be the rise time, this would be the fall time, and this really, usually they do it from the center point here to here. This would be tau. That would be the on time. Then it would repeat itself. When it comes out to the period t, then it just repeats itself. Okay? Now, this, of course, this x of t can be approximated as a summation of C of n, where n goes from minus infinity to infinity, C of n e to the j n omega naught t, and the value of C of n here is 1 over t, the integral from minus t over 2 to t over 2 of x of t times e to the minus j n omega naught t dt. So those two things are true. Now, the first derivative I take of this with respect to time, what happens? Well, when I take my x prime of t here, what do you see happen? I didn't put this value here, but it should be a. A should be the height. What happens? One derivative. Well, derivative of this part is, with respect to time, come on, it's a constant, isn't it? Isn't it just the slope of the line? It's a over tau rise, right? Matter of fact, we do this always too. Tau rise is equal to tau fall. In all digital circuit analysis, you find the one that is the fastest and you put it there, right? Be it the fall time or rise time, you use the one that's the fastest. Now, after that, if those two are the same, now I take a look at this and what do I get? I get from here to here, I have a constant, right? And that constant is a over tau rise, right? What about at this point, what happens? Goes to 0 and it stays to 0 until I get right there, right? And then what happens? Then it goes down, negative, right? Goes negative, this becomes minus a over tau rise, right? And it stays there until really it shuts off. And then it goes ahead and repeats itself, right? This is an approximation, obviously. As such. Now that's my x prime. And remember that x prime of t is equal to, that's equal to the summation of n equals minus infinity to infinity of j n omega naught times c of n e to the j n omega naught t. And of course, this, I'm just taking a derivative of that, and that means the j n omega naught comes out. And then I can say that this x prime of t is equal to the summation n equals minus infinity to infinity of my c of n. Matter of fact, let me just leave it like that for now. Let me just leave it like that. You agree with me, right? And I don't even need to put down what this is going to be yet, and I'll show you why. Now I'm going to take another derivative. Do y'all follow me on this? All right? When I take another derivative of this, now I get x double prime of t. And that's going to look like this versus t. Right here, what happens? I get a delta function, right? A Dirac delta function. And it goes from 0 to a tau rise. So this goes up to a over tau rise, and it's delta of t. It stays there until I hit this point, and then it jumps down, right? And it jumps down to a minus that, so it goes like this. This would be a tau rise. Minus a over tau rise. And then it would be delta of t minus tau rise. Stays there. Stays there until what? Well, what we can say is tau. Look, if tau actually exists from the point where it's 50% its max value to the point where it's 50%, then if you shift tau down, you'll see that this edge comes right in the beam. So this actually takes it where? You see what I'm talking about? Right here, this is really tau right here. You follow me? Class? All right, bring it right down here. This one now, the derivative is what? Negative, isn't it, class? See? So it's going to be minus, this would be a tau. It's going to be minus a over tau rise, delta of t minus tau. And finally, right here, I get a positive going pulse, and that's going to be plus A over tau rise, delta of T minus quantity tau plus tau rise. Agree, class? Everybody see what I've done here? Take a look. Derivatives, take a derivative with respect to T of this. Up, delta function, down, delta function, down, delta function, up, delta function. Got it? Just change the signs. Now, when I take a look at this, remember this is representing x of t now was equal to the summation n equals minus infinity to infinity. And take a look. I took another derivative of this, right? So what happens? If I take another derivative with respect to t on this, what actually happens to the inside of this? Just look at it. Can you see it? What's the only place where t exists inside here? Inside the exponential right there, right? What happens if I take a derivative with respect to t? What is the derivative of e to the at with respect to t? A. Well, what's A in this case? It's j n omega naught, isn't it, class? You can't read my writing. So now I bring out another j n omega naught, or j n omega naught squared. That's my point. So it's j n omega naught squared e to the j n omega naught t, but it also has the c of n, the original c of n that I'm after, right? Because there was a cn to begin with, right, class?
Yeah.
All right. You know, this is, I think, the worst time of the day to try. Outside 8 o'clock in the morning, I see everybody almost lull into a state of sedation. Probably ate lunch, it's kind of warm in here. Long day already. I'm not kidding either when I say this, because as a teacher, you look at a lot of different groups of people. I've seen this classroom full to the back. 10 o'clock classes are the loudest. 8 o'clock classes are the tiredest. And this class right now is the sleepiest. But that I've seen in a while, but you all understand what I'm saying?
Yes, sir.
Here, I'm trying to get your attention here, because you have to understand that this right here is also the same thing as saying x of t is equal to the summation from n equals minus infinity to infinity of c of n double prime, right? Times e to the j n omega naught t, where c of n double prime is equal to 1 over the period, the integral from minus t over 2 to t over 2 of my x double prime of t e to the minus j n omega naught t dt. I know it's been a while since probably you guys have done any of this stuff, but yeah.
On the graph, is tau the entire,
Tau goes from this
income or
50%
just
point to this 50% point. It's not just
Oh,
from here to
okay,
here.
I see.
It's the way it's always done. At least that I've seen. Now, this is important here. What is this? What's the delta functions? Follow me? And delta functions are beautiful because the only thing you do is when you want to integrate, you find out where they turn on and you look at the other stuff next to them and evaluate that next to them and pick it out, right? So what is this going to be? My c of n double prime would be 1 over t times, and here's what I'm going to do. I'm going to say, I see in all these delta functions a over tau rise. So I have 1 over t, and I have a over tau rise. That's consistent with all of them, right? Agreed? Then, what happens? Well, if I take x of t and I put the first, I could write all these 4 delta functions, but I think it's a waste of time. You know they're going to go in here, right? So the first delta function turns on at what time? 0. So I evaluate this when t is 0, or it becomes 1, right? E to the 0 is 1. What about the next one? Next one has a negative sense, right? And what does it turn on? Tau rise, correct, class? So tau rise, so I come here and I take that and I put e to the minus j n omega naught tau rise. Got me? I'm doing this slow. You're not writing. Do you know this? I'm just curious. Jeremiah, are you familiar with this technique? No? I guess you got Well, if you don't need to take notes, you don't need to take notes, so I'm not gonna press you on that, I just was curious if you did see this. All right, now where's the next point? That's this point, right? Here, right? So now that's gonna be what? Another minus e to the what? Tell me what the right. Minus j n omega naught tau, thank you. Agreed. And the final one is plus e to the what? Minus j n omega naught quantity tau plus t, or tau plus tau rise, pardon me, tau rise. I hope your writing's better than mine. So voila, I have that, right? Now hear me, because I'm gonna erase this. More bombs. Now I know this right here is really equal to what? J n omega naught squared times the original C of n that I wanted, isn't it, class? So I can take this stuff and divide it by J n omega naught squared, right? But I'm also going to do something. I'm going to turn this thing right here into a couple of signs in a second, but just bear with me. Man, that is one of those annoying little suckers, isn't it? All right, so let me work with this for 1 second, all right, guys? Just that part. Let me take all this out.
Wait, before you address this, a quick question. For the third delta, when it turns on at t minus tau, why is it turning on at that midway point?
Well,
instead
look,
of the slope
you notice if we shift this tau right down to here, that's the distance from here to this point.
Oh, okay, I see.
That's probably the reason they chose that to define tau. Just the shot in the dark. Good question. All right, now about that, I want you to take a look at this. Well, let me rewrite this. So I'm just looking at this quantity. I have 1 minus e to the minus j n omega naught. Is that tau rise, guys?
Yep.
And then I have what? Minus e to the minus j n omega naught tau. This is tau rise, right?
Yep.
Tau. And then I have plus e to the minus j n omega naught. And then it's going to be tau plus tau rise. Isn't it, class?
Yep.
Everybody with me? What I'm going to do is factor out this term. If I have 1 minus e to the minus j n omega naught tau rise here, I want you to watch what happens. When I factor it out of there, I get a 1, don't I? Now, look, y'all see how this is really e to the minus j n omega naught tau times 1, right? About here. These two terms here, I can look at separately and I can say this is e to the minus j n omega naught tau times 1, and there's an e to the minus j n omega naught tau here, right? But this is a minus 1, pardon me, minus 1. And then there's going to be plus e to the minus j n omega naught tau rise, right there. Y'all see how just these two, there'd be a minus there, and it would be times this, right? And there would be this. Do you follow me? Now, I can take the minus sign out front, and then you can see I can factor out if I have done this right. I have factored it out from there, and then when I factor it out from there, because that's what I'm factoring out, I'm left with the quantity. Hold on for 1 second. that's gonna be minus e to the minus j n omega naught tau, isn't it?
Yes.
Alright, and that's what this will be right here. That's what happens to this thing. Now, and you probably know what I'm up to by now. I want to turn into sine functions first, alright? So how do I turn this into a sine? Well, I factor out e to the what? Minus jn omega naught tau rise over 2, out of it, then I get e to the jn omega naught tau rise over 2 minus e to the minus j n omega naught tau rise over 2, correct? That's here. And then I'm going to take something else out. I'm going to take an e to the minus j n omega naught tau out over 2. So it's going to be times e to the minus j n omega naught tau over 2. Then I get e to the j n omega naught tau over 2 minus e to the minus j n omega naught tau over 2 here. Follow me? Any guesses what I do next?
Euler's method.
Isn't this really 2j times the sine of that argument?
Yeah.
And isn't this 2j times the sine of that argument? Sure. So really we got this phase constant. I can add these together and I get e to the minus j n omega naught over 2, and it's tau plus tau rise right there. And then I have 2j times the sine of n omega naught tau rise over 2. And then I have 2j times the sine of n omega naught tau over 2. And that is what this is. Then I multiply it by a. So I'm going to multiply it by a, right there. I'm taking stuff, and divide by t over tau rise. And then divide by j n omega naught squared. And that is my value of C of n. I'm not done yet, but you follow how I got it. I basically took double derivatives of the original waveform to get it in terms of impulses. Then, once I evaluate the coefficient for the impulse sequence, really the series that get the Cn double prime, I take that and divide by j and omega naught squared because I took two derivatives, and now I have C of n in terms of the typical functions, sine functions, right? Now please watch this part, because I know this is a lot on a Monday after July 4th, but just hang on with me. Now when I take a look at this, y'all see how I have a j squared down here?
Yeah.
And I have two j's here, so I just immediately get rid of that. I don't even bother with that. Now, my goal is to put these in terms of sinc functions, got it?
Yeah.
Now take a look at this. For this one, I need n omega naught tau rise over 2, right? Let me put this as n omega naught, and then n omega naught by itself here, because that's n omega naught squared, right? Please watch. Force yourself. All right, now I want this argument down here, right? I got a 2, so if I divide top and bottom by 2, I'm good there. And I might as well, while I'm at it, divide top and bottom by 2 again. Now, I need a tau rise, right? So I put a tau rise here. Oh, actually, it's right there.
Right.
I got a tau rise already.
Got both of them.
And, no, that's a t.
Oh, that's a key.
Yeah, now I need a tau here. Right, that's a tau rise here. I'm sorry, it's so messy. That's tau rise. Right? And that's t. And look, guys, now that's a sinc function. And that's a sinc function, isn't it?
Yes.
So I'm going to write it over here. I'm going to say this is really equal to, I need a tau. It's really equal to a times tau over t, right? Times e to the minus j and omega naught over 2 tau plus tau rise, and then it's going to be equal times a sinc function of n omega naught tau over 2, and then another sinc function, sine of n omega naught tau rise over 2. And that's my C of n, not quite, yeah, that is quite, that's it. That's it, I'm almost done. Are you with me? The next step is this. Now I'm going to tell you what's typically done. Usually they say that omega naught is equal to 2 pi f naught. Okay? Now, if that's the case, I just want you to watch me on this one, because I can work this fairly easily. I can say now that C of n here, and let me do C of n magnitude, because this phase constant, nobody cares about. That's really equal to A, what do we call tau over T typically? The on time over the total time? There's a term for this. You hear it a lot, it's digital. Duty cycle, right? Remember duty cycle or duty time? Have you not heard of it, really? You've had your digital course, didn't you? Or not? Do you remember duty cycle? Very important. It's the relationship of on time to total time of the period. And it's usually 50%, but for radar, it gets down to only 1/100th of the actual period, and it can go as much as 75% of the period too at times. So that's that first two parts. Then it's times the magnitude of the first sinc function, sinc, and I'm going to use the larger one, but here's what we do. We take and replace omega naught by 2 pi f naught. Now what do you see happening here? I got n omega naught, 2 pi f naught divided by 2 is pi f naught tau. So this becomes pi f naught tau times n, and the second sinc function becomes pi f naught tau rise times n. And that's a magnitude, and that's a magnitude, okay? I'm not out of time here. So now, if you plot this versus n f naught, now try to understand what I'm going to do here. N f naught are discrete points, right? It would be n equal 1, 2, 3, 4. What they normally do is let the product of n f naught just become f. And we look at what's called the envelope where all the spikes are under. Does that make sense? So if I do that, now I can take my n f naught here and just put f. So this is tau, and this is going to be f. And this is going to be tau rise, and this is f. All right? And what they do is plot, please write this last part, please, just do this. They plot on this axis 20 times the log of the magnitude of C of n. And on this axis, this is a log axis, so think of it like this. There's 1 log, 2 logs. This would be like 10, 100, 1,000, and so forth. So this would be a logarithmic scale here. On this scale, it's 20 times the log of C of n. Now, when you do this, if you look at this, if you have like log base 10 of A times B, that's log base 10 of A plus log base 10 of B. Does everybody understand that?
Yes.
Now that means I can break these up into logarithmic terms, sequential, each one of them, right? Well, the first term is going to be 20 times the log of A and then tau over T, right there. That's the first term. And then I have to talk to you about these sinc functions, and how you can approximate them. I'm just about out of time here, guys, because I've got to run. But this sync function, the neat thing about a sync function, if you look at it, the magnitude, here's what happens, if you can just bear with me. If I have the sync of x versus x, all right, it starts at a value of 1, all right? And let's just do magnitude. And it goes down, and where's the sign, what's the first zero? Sign of x equals 0, is it x equals 0, x equals pi, right? X equals 2 pi, and so forth. Got me on that? So this would be pi, then it would go like this, 2 pi, harder than that, 3 pi, and so forth. But if you look at this right here, this is proportional to 1 over x. It's the envelope that everything's under. Got me on that? Now, the key thing is, when this argument right here goes to 1, that's where it starts breaking down. I mean, that's where it starts going to 1 over x thing. It's called the breakpoint. Follow me? This one, the first breakpoint on this one, is going to be when pi tau f, or I mean pi tau f equals 1, or f equals 1 over pi tau. You follow me? So mark that down here. Put 1 over pi tau. Otherwise, this thing is still fairly large, because if you're down in this range, it's still about 1. Got me on that? And so we ignore that. We're going to say, and by the way, what is the log of 1? I didn't get to that. If you take 20 times the log of this, that's that, plus 20 times the log of this. Well, if the sync is 1, what is the log of 1? 0, right? So you don't care about these two until they start falling off. Well, the first one falls off at 1 over pi tau. And then it'll start falling off. You're going to have to take this on faith. It'll fall off at a rate of minus 20 dB per decade. And it's going to keep going down at that rate until you hit the next one. And the next one's going to be when this is equal to 1, or when f is 1 over pi tau rise. So then when you hit f equals 1 over pi tau rise, then it starts going down. Let me bring that in a little. Right here, make it. Then it's going to start going down at minus 40 dB per decade. I'm going to talk more about that next time, but I wanted to give you an appreciation. This is the envelope that we use in electromagnetic compatibility analysis all the time when we look at the relative signal strength. And this, by the way, normally what's done is they do this in dB microvolts right here. So they would take this original thing and divide by 10 to the minus 6. And that comes later. But try to imagine this. This is really one of these structures where this is the first break frequency, second break frequency. And if you want any value, it's for worst case EMC analysis, let's say, if you want to go at a frequency of, say, between the first and second, you want to know what the signal strength is, you take this value, 20 times log of 8 tau over t, and then you subtract from it however much further it fell. Like it's 20 dB per decade. If it's a full decade ahead, then you subtract 20 dB from it. Follow me? I'll get on to more of this next time, but I had to at least get it started. And I'm going to give you plenty of supplemental material that'll make this real and some problems. The reason I'm doing this is when Dr. Whitworth does bandwidth, he throws a number out for bandwidth, and it really, bandwidth is one of these things that means different things to different people. You have to understand how the signals behave, in my opinion, to really appreciate when you do EMC analysis what you're talking about. I wish I knew more to tell you.